We continue. I gotta say, I'm quite impressed with you guys. I've been doing this for almost 2 weeks with this many lectures. Thanks for sticking out. So we did the mission-based. Now we're going to do the scattering-based. It's kind of a different beast. I'm going to use some different techniques to get a hold of those. Is to cover schemes like this kind of high level, where you have an external photon source. So in the mission-based, it was the spin system itself, the defect center of the atom, the ion, whatnot, that emitted the photon. These scattering-based are more where we can use an external photon source to scatter off our quantum qubits and create entanglement between them. It could be something where we have a single photon source that scatters off 2 spins, for example, to entanglement, that some experiments have shown. It could be something where we have another hardware, like a photon pair source, like an SPDC source, for example, creates an entangled photon pair, and we want to map that entanglement into spins. So the 2 scattering-based schemes that we kind of will look at, so we'll focus a bit on cavity-mediated scattering. I should say that cavity, sometimes you can also just use it for a waveguide, basically. It's just a very broad cavity in some sense. That doesn't really have a well-defined or very broad resonance. So even though we're going to talk about cavities here, many of the things will carry over to it, whether it's something that is in a waveguide with strong coupling, whether it's a cavity strong coupling. We'll look at the amplitude-based scheme, where the main thing there is that you're using the fact that whether your light gets reflected, for example, or not, depends on the spin state of your system inside that cavity. We're also going to look into the phase-based schemes, which is where the light actually always gets reflected, but whether it picks up a phase or not depends on your spin state. So you can think of it as the amplitude-based is something you want to use when you have like critically coupled cavities, right? So this is basically where you say your input rate, output rate is the same as your loss rate, critically coupled. If you have phase-based, you want to go for overcoupled cavities. Okay? Basically that the loss from your cavity is very small compared to your input-output rate. The building blocks that we need is 1, we need a photon source. And we're actually not going to dive into the details of that. We're going to talk a little bit about kind of high level, what kind of photon source do you have and what are the trade-offs there. But we're not going to focus on how to model the photon source itself, because it kind of goes into a mission-based in some sense for some of these cases. I think one trade-off that we want to make here is that you can do quantum photon sources. They are true single photon sources, right? This is what we used in the mission-based schemes, but they're also really hard to make. I mean, all of these experiments that does mission-based quantum entanglement generation, you need a lab, you need a fridge for some experiments, you need laser cooling and whatnot and all these kind of things. You can also make approximate photon sources with a laser that you attenuate, for example. And that is what most experiments actually use, because then they don't need to make a third node that just emits light. But that's also where you can start to see that you can also mix and match these entanglement schemes, right? So I could use like things on a mission-based as the photon source to create entanglement with another one by scattering it off and whatnot. So you can have hybrid schemes as well. And hopefully after this lecture, you would be able to work out how those work with the schemes that you have. The spin photon interface, we're going to focus on the cavity-mediated one, and particularly what we would like to get is how can we get the reflection, the transmission of light from such a cavity when we have a spin inside it that couples to the cavity field. And then we're going to talk a little bit about detection, a bit more detailed, because in many of these cases, we run into these difficulties that we briefly discussed in the last lecture, that well, you might have one time, encoding like time bin, but the measurement you want to do might be in a basis that's difficult to do. For example, in time bin, maybe I want to measure in a superposition of early plus late. That's kind of difficult to do if I have a time bin, for example. So how do you do that? Okay, so this will be the only slide on photon sources. So we're not going to go in much detail. But again, to hammer, I just want to say, you can use a quantum system like an emission-based, right? So this is like an experiment from the Lukin group at Harvard. This is a very old one from Gerhard Rembe, the top one. And the bottom one is, so there's atoms, the bottom one is quantum dots from Peter Lodell at the University of Copenhagen. all of these emitting single photons from quantum systems, right? From defect centers, from atoms, from quantum dots. And they're really leveraging the fact that it's a two-level system. It can only emit one photon at a time. Of course, there's still the imperfections that we discussed, like, well, you have a finite length driving pulse, so you could emit two photons. It might not be exactly distinguishable, these photons, if there are fluctuations in the frequency, for example, between your systems. So that's why when they characterize these things, they're looking at these things like indistinguishability of the photons, as well as the brightness, how good are we at getting the photon out from these photon sources. But what I'm highlighting in green here is that there are true single photon sources, meaning that in principle, there's no fundamental rate fidelity trade-off. I mean, the rate is limited by our inability to collect the light, for example. But if we have perfect collection, we basically could get a photon every time we try, right? So the rate is limited by other things than that we need to do things with fidelity, at least to first order. But it is just experimentally challenging. These are like state-of-the-art experiments, right? It took people a lot of work to do this and get this out and get reasonably well single photon sources. It has made it into industry. For example, I know that Peter Lodell has a startup company selling these things and whatnot. So it is definitely also going in there. So it's not that immature, but it's just to say it's still hard. It's cost a lot if you want to buy one of these. So what most labs do is they don't use these. They use approximate photon sources, and a laser can be a good approximate single photon source. You just attenuate it, attenuate the hell out of it. Then in most cases, there's nothing. And then there's a small probability you have a photon. There's also going to be a small probability that you have two photons, and even smaller, there are three photons and whatnot. So therefore, it's this approximate single photon source. It's not either vacuum or single photon, like what you would have for quantum emitters. Forget about double excitation things. You have a fundamental trade-off between, well, how often do I get my photon and how big is my component for higher order terms? And that's kind of what characterizes all these approximate photon sources. Here I'm also counting things like SPDC source. I mean, also quite mature, right? I mean, I know that there's also a lot of work to make them better and brighter and whatnot, and a lot of cutting edge research goes into that. So it's not a done deal. Later is a bit more done deal, maybe. But it's the same thing, that SPDC source is also not only emitting photon pairs, it also emits 4 photons or more photons and whatnot. And again, it's a rate trade-off. Kind of in the same way that this, you have a small probability of getting 1 pair, and then that probability squared to get 2 pairs. And in many of the cases when you do entanglement, all these higher order things, they lead to limit your fidelity, basically. Because you can lose photons from these higher order things and then still get a heralding signal. That's the way to think of it, right? If I have 2 photons, I can lose 1, my coherence is gone, but I still get a click, I cannot herald it away. So therefore, you end up with this fundamental rate fidelity trade-off. And in most of the experiments that you see on the scattering based, the rates are actually pretty low, like hertz or something like that, and mainly limited. I mean, of course, also they have collection efficiency is not perfect and all these kind of things, but they take at least an order of magnitude hit from the fact that the photon source is not a true one. And to keep the fidelity high, they need to operate with a low signal. So that's therefore it would be nice to match these with that, and you could do, but yeah, so far that's not what people do. All right, that's what I'm going to say about photon sources. So, are there any comments or question? Otherwise, we'll move on to the scattering based. And I'm going to completely forget about this term. You can just think of it as, with some probability, I have a single photon, and everything we're going to cover next applies to that. With some probability, I have 2 photons, and at least if you want the lower bound of things, just assume that leads to garbage. All right. Very mathematical. This can be, photonic crystal that you etched holes in to modify the photonic density. So you have Bragg mirrors, right? It can be a fabric cavity, which are really true mirrors that you have, like what Gerhard Rempe, for example, is doing. It could be a fiber that makes these 2 mirrors, all these kind of things. Regardless, this is a pretty good mathematical model. It's just a single mode cavity. Again, cavities are also not single mode, right? You have iota modes, you have different resonance frequencies, but from what we're looking at, you can think of it as well, we're just close to one of these resonance frequencies, and that's what we're going to interact with. We compare out the others that you have. But that being said, of course, you can extend this to have more. Okay, so what do we need to describe this? We're going to assume that we have, again, like in the emission-based, a 3-level quantum system. Again, this is in many cases not actually the case. There will be more levels in there. We're going to assume that only one of these levels coupled to an excited state through the cavity field. And that's also not entirely true. But the nice thing is that all the things we're going to go through, they kind of carry over to when you, for example, let this one have a coupling to another excited state or whatnot. You can kind of use the same thing, very easily extended in the linear regime that we're going to discuss now. Linear regime meaning we have one photon. So if you have a laser, you turn down so it's really one photon. Even if you have actually high, a high signal of from your laser, you have 2 photon components. If you have a long pulse that you're looking at, you can still go down to like the linear regime where these 2 photons, yes, you have 2 photons in your pulse, but the chances that they're overlapping exactly in time is very small. When I say exactly in time, of course, that's kind of 0, that they're exactly in time. The time scale here will be your emission rate from your spin system here, right? So that's a time scale. The photonic emission rate from your emitter, the inverse of that's like a time window. If 2 photons arrive within that time window, then we're going to go into a nonlinear regime because now these photons are going to interfere with each other. One is going to excite, the other one is not going to excite. They're going to be indistinguishable. That's a mess. If these 2 photons are not, or the probability of them overlapping in time, that time window is low, you can basically treat first a scattering of one, and then a scattering of other, completely linear, and everything that we're going to go through now goes through. And in all the experiments that has been done so far, that's actually where you are. You have a pretty long pulse, so to speak, that it's a weak pulse. The probability that you have 2 photons within the response time of your emitter is actually kind of low. So these high order things, nonlinear things, don't really play a big role in those experiments. So you should be able with this to both understand current experiments, but also actually look into new experimental protocols that one can use for these things. And of course, this goes away. So if you have 2 single photon sources, then it's really just 1 photon. So that's nice. Okay, like in the beam splitter, we are going to look into the annihilation and creation operators here, annihilation operators of the modes. We have an input mode, that's going to be our signal, goes to the cavity. We have an output mode, that's our reflected signal. There might also be, if it's a 2-sided thing, there might also be something coming in from the other side and something leaving from that side too. And then inside the cavity, we have some kind of field, right? This is the C operator, that's a cavity field that we have. So each of these, basically, if I put diagrams on these, it will be the creation of a photon in the ingoing, the outgoing on both sides, or in the cavity that we have. And the cavity field couples through a coupling G. So this is, you can think of the single photon Rabi frequency of that kind of level. And we have the excited state can also decay outside of the cavity field. So we don't rarely have something that is only coupled to the cavity mode, but there might be some free space modes that it can couple to as well. That is this gamma here, saying that we can decay not into the cavity, we can decay into some other modes in the environment. And what you really want to care about is the cavity input-output relations. We're not going to derive them in this lecture. It will take too long. So in order to get to the fun part of doing entanglement, I'm just going to give them to you here, which is that we can relate the output mode. It's kind of like something that's reflected right off and something that couples through the cavity field. Same with this output mode here. Inside the cavity field, we basically have this Heisenberg principle Lang as well, equations of motions, that this Hamiltonian, I put a JC here for James Cummings. Actually, how many of you know the James Cummings Hamiltonian? Great. That's good. We're not going to drive that either. I'm just going to give it to you. But this is basically just describing how you do some approximations, like when we have optical fields, these are good, like rotating wave approximation. Please look this up. if you are not familiar with James Cummings, it's not, any textbooks on quantum optics, you'll be able to find it. I mean, it's also good for understanding superconducting qubits, cavity QED, which is what we're doing here. It's the same for superconducting qubits, how you read out a superconducting qubit and whatnot. It's James Cummings, Hamiltonian. If you understand that, you understand that hardware too. Well, at least some of it. Then we have that it decays with this kappa. And note, there are different ways of defining these decay rates. So here, this kappa, I have this kappa 1/2. You see I'm looking at the amplitude of the field. So kappa here is the intensity decay of the field. So that's why I have a 1/2. Others define it kappa as just the amplitude decay, that there's no 1/2. And that leads to different definitions, and we'll get back to that, in terms of how good this system is. And there are kind of two, experimentalists want to quote one, which is the highest one, and theorists often use the other one, which is the lowest one. But they're completely related by a factor of 4. So, but yeah. And that factor of 4 comes from the fact of whether you define these as amplitude or intensity decay, and the same for the gamma that I have here, whether that's then amplitude decay or intensity decay of your population. Okay, and so the decay rate of the cavity, of course, you have the input decay rate, output decay rates, these kappa 1, kappa 2 from the two mirrors. There could also be some intrinsic loss that you can add to this kappa. Then you would need also to, in principle, add like a loss operator here from the Langevin thing, but that will be like, for most things in optical, there's no real black body radiation there, so it's kind of vacuum noise that you come in with, which means, and we'll kind of neglect these noise operators as we go through, and we can do that basically because they're all vacuum, most of them. And in the end, what we're going to look at is a detection of that photon, so we don't really care what happens when it's lost. Okay, except that it leads to we're not going to detect it. Okay, so please write this down now. And while you do that, I'll write a James Cummings Hamiltonian for you guys to consider. So what I would like you to do is to use this and this. So just 2 words for those that haven't seen this before. So this is to describe my interaction with the cavity field of my spin. I'm in a rotating frame, because in principle I could go to the bare thing where, if I'm in the zero state, that has an energy, and it will pick up a phase, right? That goes as e to the I omega of that transition, that state, times t. Well, I'm going to redefine, so I don't know if you're familiar with it, but you can always go to basically a rotating frame where you say, well, my standard basis gets there just following that, frequency. So I don't want to keep track of that phase that it requires from just the bare frequency. So in the experiment, you have a lab frame and whatnot, kind of like that. It's respect to your lab frame. Here I'm defining my lab frame with respect to these things. When you go to an experiment, you kind of need to be a little bit careful of how these theoretical things carry over to what they do, but usually experiments are quite good at doing that. But that's why I, for example, do not have any energy of the cavity field in this Hamiltonian. That's because I'm basically in a rotating frame with the cavity field, see? And now the phase that I pick up with this E, is basically detuning, where I say, well, it's the frequency of my excited state. I mean, I put h bar to 1, by the way, right? Otherwise, it should be h bar on all of this, because of it is, of course, energies and not frequencies that I have. But in the end, h bar will factor out. We don't really care about it. We don't want absolute things here. So this is basically the energy difference between exactly this. We have in 1, we add a cavity field. How close are we to actually E? That's our detuning. We have these operators here, which is just basically exciting or de-exciting the excited state. Sorry, the spin. Defined this way. And maybe one thing that would be good for you to remember is the commutation relations between, so now I'm just writing A here, but of course it also goes for C and B. These are all bosonic annihilation and creation operators. So they have the same commutation relation. And do anyone remember what this is? Yes, exactly. So this is 1, right? So meaning that A dagger minus A dagger A is equal to 1. you can use that to manipulate terms that have multiple creation operators. And with that, the task is clear. How does this look like? This equation, when you plug in the Hamiltonian and work out the terms, what equation of motion do you get for the cavity field operator? Question? Answer? Or, all right, nice. Then please come up and write it.
It's like that term, that minus I star. Right?
Yes, and then the rest is the same. Exactly. Yeah. So I'm just going to add the terms here. So we're going to put C dot equal this, and then exactly we have exactly the same thing. Kappa half C, kappa 1 A in, kappa 2 B in. Right. If we need to solve this, we also need an equation motion for that operator, the sigma minus. So next task, what is the equation of motion for that? Here, you basically just need to use this one. So now insert it in with Hamiltonian here. I will add by hand the gamma. It will be there as well. Actually, the gamma that you have will enter exactly the same way. You will just have gamma 1/2 and then the operator. Right? So in our case, it will be gamma 1/2 sigma minus. But then you need that term. So now you basically just calculate that term and give what it will be here. So, okay. So we want I just want that, what that term is. Here.
Yeah, this bit becomes a sigma minus I minus sigma minus, right? That's because with this, right? So any the commutators that are like sigma minus, like sigma, this commutator is 0, with all the terms that are like sigma minus sigma for this, you know, you've got like, and I will like get these, right? If they're in a product, then they just, you know, you get a 1 over here, so 0. And this term here, EE, that's the same as writing like sigma plus sigma plus, right? Also sigma minus sigma, EE is like sigma minus sigma minus, right? Yeah.
Sigma minus sigma plus, or sigma plus sigma minus, sorry. No?
Is that true?
Yeah, no.
The commutator of sigma is like close to sigma.
This is true, but I'm not. All right, let's forget about it.
Yeah.
So this is the same for me.
Yeah.
So we need to take it like this. So this one continues with this. So it's just like this, right? And so it becomes like, I don't know what the definition of sigma z is.
Just write it out. Then yeah.
Yeah. When there's like plus or minus, so this and c. And then that's where it's.
Yeah.
Sorry. Indeed. So you can always, maybe it was actually not too big of a help that I gave you this. You don't need to use commutation relations. You can always just write it out and say, what happens if I take E sigma minus, and then indeed just write it out. It's E minus is 1. E minus 1 E, 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 and you can see that that is 0, and that gives minus your sigma minus, these kind of things. And you can do the same with sigma plus sigma minus. So my apologies, maybe not too much of a help to look at commutation relations, but you can also just work it out, basically. Okay, so we just minus, and you're right, this here usually is something we define as sigma c when it's one minus the other. So we could put this in and say, okay, sigma c and minus gamma 1/2. Oh, there should be a c here. Minus gamma 1/2 sigma max, like that. Here define sigma c as e minus 1, 1. All right. But of course in here, I've just inserted this minus gamma 1/2. In principle, if you want to be really strict about it, it should be Heisenberg-Langevin equations. I also need a noise operator that goes with this decay over here. But again, for what we're working with here, we can just forget about that, actually, because we're not going to matter for us, because we are, in the end, you can think of this, we are again going to herald on detecting that photon. If we decay somewhere and don't detect it, yeah, something will happen to the system, we don't really care. Just got thrown away anyway. So therefore, I don't really care about it. If I had to keep what's happening when we lost the photon or not, then I need these noise operators to basically keep everything bounded, right? That it doesn't, that I keep my system physical. But for this, we don't really need to care about it. Okay, now I have a bit of an issue here because now I have another operator, sigma c, so I can still not solve my equation for motions, right? Because now I have another operator that also depends on time. So I need to do another equation of motion to solve this. But this is where we're going to make a bit of an assumption. By the way, I think there should be an I there. If we have a weak pulse, if this pulse is long, meaning that you can now think of, I have a single photon, right? So let's use the Fox state that I did before. This is a single photon, but actually it is, something like this. It is a superposition of this photon being created instantaneous in time over a certain envelope, right? So when you have a photon, there's a certain envelope of that pulse. This is this f of t. And I'm saying now that that photon can be anywhere here, right? So the distribution of this in time would be, this is the probability that the photon is at that point in time. Maybe it's a Gaussian pulse, for example, that I come in with, and it looks like this. So that would be your f of t. Now, if that pulse is long, it's normalized, of course, the photon is there somewhere, then this is going to be a very broad thing here. The probability that the photon is in a small time window is kind of low, right? Here the time window, if I ask what is the probability that my photon is here, and this delta t is sort of like, it's proportional to 1 over gamma, let's put it like that. We also have the g that can complicate things a bit, but that's kind of what sets your time window here. But if I'm saying that my pulse is long compared to that response time, the probability that I have a photon in the cavity during this interaction is actually kind of small. What does that mean? That means that the probability that I am in a excited state is also kind of small. And you can kind of see this kind of, if it's really long, it's really like flat, right? So it's kind of like, I have a very small probability, it's kind of constant to be in an excited state as time goes on. I'm going to use that because I'm going to say, well, this here is kind of just, projection onto 1, let's say at time 0. I mean, when we start our thing. So if I start out in state 1, I'm going to stay in 1 pretty much all the time. There might be a little bit of adiabatic kind of thing of an excited state, but it's so small that, I mean, again, it's kind of just mathematical approximation, right? I could say, well, this operator, I should keep, it has some contribution from the E term, I'm just saying it's small compared to the contribution of that. So it's okay for me to just kind of say it's approximately a constant. I don't need to keep it, the quantum mechanical things of it anymore. It's a classical kind of constant number. It has a certain value, basically. And that value I'm setting to be basically, well, did you start out in the 1 state or didn't you? Right, so if you start out in the 0 state, it's 0. And if you start out in the 1 state, it's 1. All right? That simplifies things a lot, because then I don't need to solve for this one anymore. Just take that and say it's this. Okay, so remember the approximation I did here was that, well, you know, the probability to actually find the emitter in the excited state is very low all the time. So a long pause. The other ways you can get to the same thing, if you assume this to be closed, actually, then you could get the same and whatnot, but it is a pretty good approximation for the experimental parameters that we care about. Okay. Now, we can actually solve these. It's really difficult to solve this in time domain. So what we want to do is that we move to frequency domain to solve these. And so let me just move this. I don't care about that anymore. And let me just write these again up here. So we have this one, minus G, sigma minus, kappa half, C, plus square root kappa 1, A in, kappa 2, B in. And we had the sigma, which was minus I delta, minus gamma half, minus E, IG, C. Okay. So how do we go from time to frequency? What transformation do we use? Fourier transform, exactly. So I'm just going to define basically that, you know, this operator in frequency is just the Fourier transform of this one, right? Remember that if I take the Fourier transform of, you know, some operator A of t times if I type a constant, what is that? Yeah, just move it up front, exactly. So it's just a constant times the Fourier transform. Let's see, is there anything else you need? Yes, you also need. So this is just k times f, well, times a omega. If I take the Fourier transform of a derivative, I don't know if you know this, but I get this vector out in front. It depends a little bit how you define the Fourier transform. Sometimes you have 2 pi's floating around, but you can just use this. Okay, so why do we want to use the Fourier transform? That's because we don't want to deal with these time derivatives. We instead just want to have this into a set of linear equations that we can solve very easily, right? And that's when I talk about the linear regime. When I say the linear regime, this is what I mean. We end up with just a set of linear equations that we can solve. And to do that, we have to assume that it was 1 photon at a time, and that we had like this more or less negligible population in the excited state when we do it. But that's a good thing. Okay, so using these, can you derive what C of omega is? And give an expression like that, I mean, A is just A in of omega, B in of omega, right? Those you just keep as A in and B in. We're going to express them in terms of those. But yeah, what will the cavity field be in this? So, sorry, forgot to say we of course still have this constant, right? P1. wait, this is a constant, P1. You don't need the input output relations for right, but here you just use the fact that you're okay to express everything in terms of A in of omega and B in of omega. You just define those. Yep. Yes. So sigma is this, but for this calculation, you basically want to eliminate sigma. Thanks. Yeah, I understand. Yeah. Go ahead. That's awesome. Yeah. I very much agree. So, I mean, quantum mechanics is just linear algebra, right? Okay, it's actually the same that I have written here. I'm just going to do a few things here. I'm going to move the gamma, pull that through here, so it goes up there. I'm going to take the kappa and move that up here, so it goes up there. So then it means this becomes basically, I'm going to take the 2 as well, and the 2 here as well. So I basically get 2 divided by kappa. I'll write it a little bit down. Times kappa 1 in kappa 2 E in, and I'll now have 2I omega over kappa plus 1 plus, I'm going to write this C P1 over 2I omega plus delta plus 1. And here, yep, I've defined this C. Oh, there should be a 4 here, which is G squared over kappa gamma. And yeah, that should be, oh, I need that delta here, so of course. And the gamma here divided by gamma. This one. Okay, so why did I write it like this? Seems unnecessary. Is introduce one important parameter, which is the cooperativity. This is the C. And you can see the cooperativity is basically the ratio between your coherent coupling, G, and your loss rates. Kappa, the decay of the cavity field, gamma, the decay of the excited state. So the cooperativity is saying something about how strong is your coherent coupling compared to your incoherent couplings or incoherent rates. And in many cases, you want cooperativity larger than 1 to be able to do great things. And what we'll see is that the quality of your scattering, I mean, how good your entanglement you can make with these things, will end up depending on the cooperativity. So that's why in many of these mental papers and whatnot, you care about the cooperativity of your system. You look at it. Another thing that we can extract from this here is that when you define like that, you also have omega in units of the cavity line width, or the K rate here, kappa, and we have omega and delta in units of the the excited state line width, gamma. So that means that that kind of intuitively makes sense, because what is omega actually? What I said was in a rotating frame with the cavity frequency. So if I put omega to be 0, I'm on resonance. This is basically the relative frequency compared to your cavity resonance. Omega of 0, meaning that I'm exactly on resonance. When I start to be off resonant, as you know, if I'm coming to a cavity and I'm very off resonant, I'm going to be, completely reflected. If this term is very, very large, this is 0, right? Meaning that there's no cavity field. I don't enter the cavity. And as you'll see from the impeller operations, I get completely reflected. But of course, what does it mean to be off resonant from the cavity? Well, it only makes sense in the units of actually the cavity line width. If I have a broad cavity, I can come in with a broad pulse and I will still fit the cavity, right? If I have a very narrow cavity, then I need a very narrow pulse to fit it. So therefore, this term only depends, and it's really in the units of kappa that this matters. Same thing here, this is basically my interaction with my spin system and my excited state. So what is the, length scale that matters there, or the frequency scale that matters there? That's of course the natural line width of that. If I come in with something that's very broad compared to the natural line width, I'm not going to interact with it. If this is very, very large, this delta, or if this omega is very large compared to that, this term is 0. And the only thing that enters with the coupling to the emitter is the C here, right? That's the coupling. So if this is 0, I'm basically just looking at an empty cavity. So this is telling us that, okay, how broad my light that comes in is compared to the line width of the spin system, that matters for how strong interaction I'm going to see with my system. And as we would expect, these are the scales that we have to do. Right? And just another one to keep it. So here I put a little bar on this back again, because in principle, this here is 1 for spin state 1, it's 0 for spin state 0. So if I come in with a superposition of a spin state 0 plus 1, I can now go and completely calculate what is the cavity field from the 0 component and for the 1 component, all keeping it as a coherent state, a coherent superposition like this. Right? So basically, just because 0 would break this to 0, 1 will break this to 1. Okay, yeah. All right. Great. You might also already start to see what happens, right? That in principle, people think differently about how this interaction is, but one way of thinking of it is that, okay, I have a response from, if I don't have the 1 state, I just have a response from the cavity, right? No spin state. I just get this kind of cavity field. I can calculate the reflection to that. When I actually include the spin state, it's kind of like I'm now interacting with a shifted cavity. So my resonance system is no longer just a bare cavity resonance, but now I'm actually shifting my resonance because I have an interaction with the spin. So it's a coupled system I interact with. And that's where the response then gets different. But it leads to some quite nice things. So let's look at reflection transmission. Now let's assume that we don't have any input field. So Bn is 0. Just put it to be 0. Now my reflection will be determined by this. This is the amplitude of reflection though. So keep in mind that people usually define reflection as the intensity. So you would need to take whatever is in front of this and square it. Transmission is the same. But we can now start to look at this, and let me just check if I have in the next one. Yeah. We can now start to look at, for basically a signal that comes, we can define the transmission and reflection from these cavity input-output relations. Okay, so let's look at that, and let's make it simple for ourselves. So let's assume it's a balanced cavity, critically coupled, you can also say, so because if I say nothing is coming in, and I'm just saying that the output now is just my loss field, so I'm not monitoring it, this is basically a critically coupled cavity. And I'm saying now that kappa 1 is equal to kappa 2 is equal to kappa 1/2. Critically coupled. Let's assume we're on resonance. Delta omega equals 0. Then what is the reflection if I'm in qubit state 1? What is the reflection if I'm in qubit state 0? How does that look like? And you guys should derive that from, if you didn't take notes, this, or actually it's over there as well, you can use it there. And whoops, but this is how we want expressions for how does the output field look like in terms of the input field. You'll basically find that there's some constant times the input field. That will be your output field. That constant is your reflection. Same thing you'll find for transmission, but focus on the reflection because transmission you can say is just 1 minus that in principle in the square. So my question is, in this case, yes, what will happen if I'm in the 0 state? What will happen if I'm in 1 state? Yeah. Yeah. Sorry? If I'm, and in what spin state? It depends on the spin state, what the reflection will be. That's correct, yeah. So indeed, you should kind of find that if you're in the 0 state, reflection is 0. Kind of what we expect for a critically coupled cavity, right? That send something in and just lose it on resonance. That's good. What happens if I'm in the 1 state? The what, sorry? Yes. It's this one. Yes, I think we got a little bit the answer here. Will be something like this. Hope that matches what you got. So indeed, we see that if P is 0, this is 0. No reflection, critically coupled, we just lose light. If this is 1, if C is high, is big, we're actually going to get full reflection, right? If it's not big, then we'll have some reflection, but also some transmission. This is a paper from 2020, so a little bit old, but to be honest, they're still doing the same thing. So this is where they have a silicon vacuum center in a non-photonic cavity. They reflect light from it, and this is their reflection. This is the laser detuning. They're not exactly operating on resonance and whatnot, so because of some complications we'll get into. But the fact is that what you're using is that you can have a very big contrast between whether in one spin state or another to this reflection. This is a critically coupled cavity that you're looking at. So this is exactly what you kind of derive now, that if in one spin state, I mean, it's not exactly 0, right? Because there are also some imperfections, but you can really be, okay, I get nothing back. In the other spin state, I get everything back. You shouldn't, right? But okay, it depends on how they actually normalize their experimental data. Yeah. I mean, you have noise on top of it, right? So you always have fluctuations, and I guess that's what you can lead to in principle, a reflection higher than 1. Okay, so what did they do in that paper? They actually used this to entangle a photon with their spin and transfer the information of the photon into the spin. So entangle and then teleport the information in. And that's kind of what we're going to look into next, which is how can we use this, the fact that from one spin state, we can get reflection, and from the other spin state, ideally we have no reflection. So just assume that. Forget about the small imperfections here. We'll cover those later. How can we use that to basically generate spin-spin entanglement, which is what they later went on to do in 2024, using exactly the same thing. And that is what is called the amplitude-based scheme. I think I'll give the protocol. That was a little teaser. But since it's been an hour, let's take 10 minutes. Think about whether you can, well, how you would do this kind of entanglement. And then we can come back in 10 minutes and see if we kind of arrive at the same protocol. All right, so let's reconvene 20 to 1. Thanks. Okay, let's start again. So sorry for the delay. There were some great questions during the break, and I actually wanted to follow up on that. So again, just to iterate, what we've done so far is that we linearize these things, right? So it only applies in the linear regime, which, as I discussed before, you know, if you have photon pulses coming in, I don't know if everybody can see this, but it's again the same that a Fock state is, in reality, it has a certain mode, right? It's a mode that we define, and we say that's a photon in that mode. That's our Fock state. That mode is, for example, an integral over a temporal function, f of t, that is basically the envelope of that photon with instantaneously created photons at every point in time. A two-photon Fock state would be a double integral kind of thing that we have here. And that's where I say that if this f of t is very long, then the probability that we'll have two photons within the same time set by a basic emitter. And now that we defined the cooperativity, we can also say that that timescale is actually not 1 over t. It's 1 over gamma. It's 1 over cooperativity times gamma. So the bigger the cavity, the faster the response. As long as these two photons, the probability of those being within the same time window as that is small, that's where this linearization works. We really think of it as like a perturbation approach, right? That we're taking the leading order, which is when these two photons are not overlapping within that time. There's a correction with the probability that they are. That correction is small when you're in the regime, therefore these gives pretty good results. However, these are good for experiments that, like these guys, and when we want to entangle, it's the regime that we're in there and it works. There are also other experiments that are nice to do, because you can also use these things to sort pulses. And for example, say, well, if I have a combination of 1 and 2 photons coming in, because we can show here, I can get complete reflection, for example, if in one state. But if I have 2 photons, that's no longer the case, is they're overlapping in time. There I exactly need the higher order terms. So experiments that are looking at, for example, photon sorting with these things, you cannot use these equations, because then you care about then you regime where you care about these higher order terms, because it's a very different parameters that you're looking at. And people also ask, like, where can one go to look a bit more into that? For example, all these higher order terms. I recommend that you should, at least from the research perspective, Klaus Møllmer from Aarhus, I think he's now in Copenhagen University actually, he has done some pioneering work in this field, and he is very good at describing this. I think he also has some recent works together with postdoc Andreas Kilevich. So I'm just gonna let's see if I can get a window here. Okay, I need to work the double screens here. Okay, I need to stop sharing, I think. Okay. Close that. Do like that, okay. Okay, and let me see if I can. Andreas Kilevich. Alexander. So this guy, input-output theory with quantum pulses, quantum interactions with pulses and radiations, some recent work that are kind of doing go beyond the linear regime. That's where you kind of need to do numerical works and whatnot. But you probably will, which is what I very much like about what they're doing here, is that they go down and say, look, we're still just in cavity input-output relation. So even though you don't have a cavity around this, you can always model this a fictitious cavity around and multiple cavities around to capture all of the different output modes you can get, even in free space and whatnot. So it kind of stays with a little bit what we're doing here, but I definitely recommend if you want to dive more into details of this, you start here. I think that's a good, maybe they're a little advanced, these papers, but then within them are good vetted references from Klaus Møllmer on where you can get the durations of what they're using. So I would start there, if it's it. All right. Okay, but again, for what we care about, entanglement generation, we should be okay with the linear regime for now. First order perturbation, you can say. So how can we use this to generate spin-spin entanglement? This is the protocol that these guys used in this paper in 2024, where they did it over a network in Boston. It is just, not a single photon, it's a attenuated laser. You bounce it off one, you send it to the other one, you bounce it off that, and you detect it. That's basically what they did. So you take Alice and Bob, they independently prepare the SIV, that's what they use here, because that's what you can couple to a cavity, or nanophotonic cavity, that is. Put it in an equal superposition of 0 and 1, and Here, I'm just saying Alice prepares a single photon in state early plus late. Think of this as it's a laser, right? So she's actually preparing vacuum plus a small probability of a photon 1e plus L. But since we're going to detect it at the end, we don't care about the vacuum term. It's just going to lower our rate. Okay, the early time bin is scattered from Alice's system. Then we do a rotation of the spin states, such that we flip 0 and 1, after which the late time bin is scattered. And here, again, assume that we're in the case where if we're in state 0, we don't get reflection. And then step 2, the photon goes to Bob. Bob does the same thing. And then after that, we measure the photon in a so-called time delay interferometer, because we have time bins, and we need to erase which time bin the photon was in. Otherwise, we won't get entanglement. The way you do that is through this time delay interferometer, and we'll go through that. And then, a successful detection, meaning that I got my photon, prepares the SIVs in entangled state. Okay. Whoops. So now we're going to do a little bit kind of similar to emission schemes. We're going to go through these steps, kind of make sure that we understand how we get entanglement from it. So I will also note one thing, that actually what you derived, this C of W, in the linear regime, it's quite general, right? So when I said, assume everything is on resonance, omega is 0, delta is 0, whatnot. We don't have to do that. Also, what does it mean to have omega 0? It means that we have an infinitely sharp pulse in frequency, meaning an infinitely long in time, which is of course not the case. So just as I wrote before, that in time, a photon would be some f of t, a dagger t vacuum. Of course, with the Fourier transform, I can also get this in a Fourier space, and it's some g of omega, a omega dagger vacuum. G and f are related by Fourier transform, right? So meaning that if I have something that's very narrow in frequency, it's very broad in time. Why? That's another motivation for why are we then in the linear regime actually? Well, because I want this photon to fit within the line width of my emitter. Right? Because if I have a photon that's broader in frequency than my emitter, we know from the term down here, if this omega is very large, I'm not going to see the emitter. So I'm not going to entangle. So that's why you also naturally want to be in the long pulse regime for the entangling schemes, because if you want a high fidelity of the action reaction, you need your pulse to be very narrow in frequency, meaning long in time, meaning that, yay, the linear regime kind of works for these things here. But if you want to calculate actually what is the, take into account the finite width to get what errors do you get from that, for example, you can just use this. You just now need to integrate over different frequencies, right? This is kind of what happens per frequency. You get C of frequencies. So now if you want A out of frequency, you just need to integrate over the different frequencies where you have different reflection because you have omega in there on that. So you can still include that in here. We're just not going to do it and just assume that we have an infinitely sharp pulse, meaning infinitely long at this point, because it's just easier. But nothing breaks down in what you have when you don't have that, except when you go out of the linear regime. All right. Okay. With that in mind, let's get to the protocol. And you don't need this. You just need to remember that you're now saying that you only have reflection if you're in the one state, and if you're zero state, you don't reflect. Right? That's what we're showing here. Okay, so let's just look at Alice's side and forget about Bob to begin with, because step 1 and step 2 just happens on Alice's side, right? We don't care about that Bob also has a SIV system. We don't need to look at it. So on Alice's side, she starts with this and a photon. So how does this state look like after step 2? Yeah, indeed. So let's see if I just want to not confuse notation. Let's keep it. That's fine. Okay, yes. So indeed, if we were in the early one and we scattered, then we're lost. One thing, however, is that I did do a flip in between. So if I saw in the early, I will now be in the one state. I don't know about it. Yeah, exactly. And this will be 0. This will be 1, and this will be 0. But yeah, I mean, the only thing that goes through is indeed you're saying, okay, if I'm in the early, I'm going to be lost from 0. And then after the flip, it will be 1. I had lost it. If I'm early and in the 1, then I'm actually going to be reflected. When I flip it, it's a 0. After the flip, if I'm late and I'm in 0, I'm lost. If I'm late and in 1, I'm get survived. Exactly. So if I say we are going here rather than detecting full in the end, any lost term will never lead to a click, right? Forget about dark counts. So that means that this term and this term, they basically just limit my success probability. And that means that if I go through and say I in the end going to rather than a click, then what I'm going to get is this state. Zero. Let's see, E plus 1. Is that correct? 0 should be 1. Yes, so that's the early, and late should now be that I flip from the 1. Yes. So then I'm flipping this 1 too, I guess, right? This is 0. This is 1. Oh, that should be okay. So this is the only thing that survives when I have a photon. And what is the probability with which I get this? It's 50%, right? So 50% probability, I end up with a state that now is entangled between my spin and my photon, and the photon carries on to Bob. Now I'm going to do exactly the same thing on Bob's side, and Bob starts with this superposition again, and the same thing will happen. If it's an early photon that comes in and Bob's state is in 0, I'm going to lose it. I'm not going to detect it. If it is in 1, I'm going to keep it. It's going to be reflected. So the exact same operation is going to happen in Bob. The success probability is also going to be 50%, right? I'm just matching what is the probability to be in 0 and have the right photon. That's 50%. So in the end, what I will end up with, I hope you can convince yourself of that, is that we'll end up with 0, 0 E plus 1, 1 late, if the photon still survives. Sorry? Oh, okay, I'm normalizing after I forgot about, so I'm saying here I did normalize the states. With probability 25%, I'm going to get this state. With probability 50%, I'm going to get that. So this is just Alice interaction, then I put bars on top, also 50% chance that I get it there. I end up with a 1/4 probability that I actually is going to entangle these guys. Right, so that's the downside of the amplitude-based scheme. It's not deterministic. But in this way, I can generate entanglement. But now actually, it's not a Bell state. It's more like a GSC state, right? Because it's 3 systems that are entangled, the photon and the spins. So now I need to do this measurement where I decouple the photons. So mathematically, that's kind of easy, right? I just want to measure in a combination of early and late. But these are really like physically separated pulses. So how do I interfere them? I need to put them in a time delay interferometer, and you can make it in different ways. This is one way of doing it. And I think I made the beam splitters in the right way. So I think one thing that you can always check experimentalists and theorists, right, is whether they turn the beam splitters the right way, that indeed reflected light goes like that and not the other way. I think it made it here. But the idea is basically the pulse come in, 50-50 beam splitter, so 50% chance it goes through the short arm and goes on be detected. 50% chance it goes into the long arm. I'm going to add a delta t, which is exactly the time between these. And then I'm going to detect what mixes here. So yes, what is the probability that such a measurement here will erase the time bin information from my photons? Remember, I come with an equal superposition between being in early or in late. So just think classically what can happen when you come with a photon, right? This is not a deterministic measurement. Sometimes I will fail to erase the time bin information, and I guess I'm asking, indeed, what is the probability that I correctly erase them? What needs to happen?
The early one needs to be reflected.
That's exactly correct. Yes. So I mean, there's a 50% chance that the right thing happens with my photon. So there's a 50% chance that I'm going to actually erase it. The other thing that can happen is, of course, that the early goes through right away, or the late gets in the long arm, right? And then will not have interference. So this probabilistic, that gives me another 50% chance of actually doing the entanglement, because if I don't erase the rich path, I'm just going to project onto either that or that state, no entanglement. Is there a way to make this deterministic? I'm asking you. Sorry? A variable delay? Yeah, I'm not. You still need to interfere these definitely together and add. You need to deterministically basically delay one and not the other. So yeah, in the sense that if you can control phase, you can make a switch to whether the photon goes in one arm or the other. So if I add a photonic switch here instead of a beam splitter, I can make this deterministic. Basically, just when the first one comes in, I route it up to the long arm. When the one it goes through. And how you do that in practice, I guess, is with a variable phase in an interferometer that you do. So yeah, in principle you can do that, but it's difficult. Switches are lossy and not. I mean, you can have fast switches, but they're also usually lossy. You can also have slow switches, but then these time bins need to be separated by a lot. And so in the end, for most experiments, they just take the hit of a beam splitter. That being said, you could do it if you want. Yeah. So what is the photonic basis states that I'm measuring in when I'm successful? Interfering these two, I basically just get superpositions of early plus minus late. So what I'm doing, if in successful measurement, is I'm basically projecting onto that basis. So you can yourself kind of just express early as the plus minus combination, the one that's the plus minus combination, showing that I'll get different Bell states depending on the outcomes, but it's just a phase. So yeah, that's what I'm doing. Just erasing the which time bin information. Okay. So what is success probability? We had a 1/4 of just the entanglement generation interaction with the spin, right? 1/2 from one, 1/2 from the other. We also have 1/2 of the detection. So we get like this 1/8. And then we have, of course, transmission. Here, eta, again, being all loss in the interaction with the cavity. And exponentially, you probably need to go on chips. You need to go from fiber to chip, coupling losses. You need a circulator to basically take your reflected light and separate from your input light. That has loss, maybe 80–90% transmission from that. Then the fiber itself, you need to go frequency conversion, which they did in this experiment on the Boston. That has some efficiency. Telecom, you need to go back again to 737, which is IV, another loss. Back to chip again, circulator detection. So this eta ends up being quite low. But it's just like this. Fidelity, we didn't really go carefully into, and we're not going to do it. Sorry, yes, this is 1 minus, it's indeed another typo here. It's infidelity. So the infidelity goes as 1/4C, roughly. What I'm just saying here is that carefully, you need to, as we saw from, let's see if I could go back. How well your interaction works depends on your cooperativity, basically. And you end up, when you take also these finite thing effects and whatnot, your fidelity will always end up somewhat scaling with your cooperativity of your system. So this is where your cooperativity, the better it is, the better this works, basically. There are other things that can limit the productivity as well. I mean, you can also have reflection that is not from the spin itself, but just because you have bad mode matching and whatnot. For atomic experiments, for example, that is very often the case when they do these things, that the mode matching is not good. So you input pulse in your cavities, meaning you just get reflection from everything and whatnot. You can then play tricks by also looking at, if you have access to it, looking at transmission instead of reflection, and you can play tricks there. So there are ways to work around it. In principle, this general thing that you have here allows you to look into all of these things, because you can have input, transmission, reflection, whatnot, different cooperativities, whatnot. You can tune around these things. And when they do the experiments, they do careful optimize these where you want to be detuned, both from the cavity and from the spin transition, transmission, reflection, what is that you need to look at, given the parameters you basically have from fab on your cavity and whatnot, right? Principally, you should be able to do all of that with this. But just so the simple thing that we went through now doesn't capture all of that, but that was basically just to get the gist of how to generate entanglement with these. Use the fact that you're selective reflection and the fact that you have a finite success probability. Indeed, remember the fidelity is not this. This is the infidelity. Fidelity is sort of like 1 minus this, you can say. But it should be infidelity scales like that. And yeah, as I said, what we didn't include, we had a lot of things we didn't include. Non-perfect single photon sources, multiple photons from the laser, right? You have this rate fidelity trade-off that we started out with saying. That is still there. You have defacing of your spins. You have finite bandwidth, pulse length. This is what we just discussed here, that it's not an infinitely sharp pulse that you have. It has a finite width. That means that it will be different reflection from different parts of the pulse. So the pulse is no longer the same. Dark counts, not optica, but optic phase instabilities. Also is not in, for example, silicon vacancy centers. You do have coupling from 0 to an excited state as well through the cavity. So it's actually not just one that couples, the other one couples too. And but with different detunings, depending on how your level are arranged. I mean, what magnetic field you have, the splitting between these. Basically, you care about the optical transitions. Are they the same or not? They're not exactly the same. You can tune them with magnetic field, but only up to a degree. And then you basically have reflection from both of them, and then you need to play around with the detuning from these reflections. So basically, in such a case, you would have something where this is P1. You will have something where this is P0 with a different detuning and a different cooperativity that you have here. But again, exactly the same thing. As long as you're in your machine, this is enough for you to also cover those things. And you can still use that to do these. But that's what ends up also limiting these guys. I mean, this is what you can see here, right? You actually have both regimes where these couple and lead to no reflection, because they're both this one state and this 0 state have a coupling to the excited state. They're just at different frequencies. So the question is, are they separate enough that you can have a good contrast, which will basically be, again, how good you can perform your gate. And there you can play around with the magnetic field and whatnot. So then we need to go into also the details of the spin system itself, which we didn't cover here. How do these shifts? Okay. Yeah, imperfect gate operation, of course, as well. Something we maybe didn't cover before is every time we do a rotation of these spins, it's a gate, right? How well can we do it? Depends on our capabilities. Dynamical decoupling, all these kind of things, all comes in. We want to do this. All right. We just have time to go through the case when it is, not the amplitude, but the phase. So this is critically coupled. I should say, this is something that we've done with atoms. I don't think anyone has done it with solid state systems, for example. At this point, they always use amplitude-based because it's just, again, it comes into how easy is it to tune your parameters so you have a good contrast between spin state 0, spin state 1. And for some of these nanophotonic cavities, it's just easier to tune it when you just care about having the amplitude, meaning the probability of reflection, being very different, and not that also you need, like, for the, what we'll see from the phase place here is that here you want both spin states to reflect, but with a different phase. So there you need the reflection from both spin states to be the same, but the phase to be different. So that needs more constraints to how you can tune your parameters. The way to go through that is basically just take your overcoupled cavity and say now it's really a single-sided cavity, right? So kappa 1 is equal to kappa. Again, just assume everything is a detuning. We are not going to go through it now, but you could do exactly the same as we did before. Just take your C, put in 0 and whatnot, and what you should get is that now your A out looks like this. So what does that mean? That means that if I'm not coupled, I get reflected with a phase of pi. So it says A out is equal to minus A in. And if I make this very big, this C, this goes to 0, and I get reflected without a phase. So I can get a pi difference between whether I'm from 0 and whether I'm from 1 in the perfect limit, right? And then you need to play around with detunings and whatnot when you're not. By the way, I should actually say maybe it's not that bad. So these amplitude-based gates, they can get pretty high fidelities. So like the fidelity of such a entanglement operation could be up to, in the 2020 paper, it was above 95% fidelity. In unpublished results, I think they're up at 99. So it actually can work pretty well, these things. The phase space has not really been shown in that system yet, but I know they're working on it. Okay, so the key thing here is the phase is that here we have a single-sided cavity. We want the reflection actually to be the same, but the phase to be different by a factor of pi. And if it's not a factor of pi, you can also play tricks and whatnot, but we're not going into that. The protocol is exactly, it's a little bit different here. So if you wanted to make entanglement, we take Alice and Bob, and now they just prepare the state in 0, not the superposition speaking with. Alice prepares a single photon state, E plus L2. Then she scatters the early time bin. Then she does a rotation, brings 0 to 0 plus 1, and then she scatters the late time bin. And the same thing is done at Bob's side. So let's just quickly see what happens here. And don't worry, you're off the hook. I'll just show it real quick. So I come in with a photon in early plus late, and I start with just the 0 state from Alice. I'm gonna scatter the early one, okay? That just gives me minus early, like this, high phase shift. I'm going to do the rotation of this spin, so that now means that I have square root of 2, square root of 2, then I have early, late, the plus state, right, 0 plus 1. Now I'm going to scatter the late one. So what happens? Well, for the early time bin, nothing happens, right? Because that already scattered. So I still have early plus. For the late thing, I need to make sure that, well, if I scatter from 0, I get a phase. If I scatter from 1, I don't. So what I will get is basically late this, right? The late one gets a phase, it goes to 0, doesn't get a phase within 1. Okay, let me put this out here. And I don't care about a global phase. Just do it like this. And I'll say this is the same as early plus late minus. So I entangled my photon and my spin now, right? And I can now send the photon to Bob and do the same thing. I would get that, and then I can measure again my time bin photon in the spaces with my time interferometer, and I'm done. Okay. So my probability is different because this is actually deterministic, right? I reflect all the time, so it's just loss. The 1/2 comes from the measurement being probabilistic. Principle I could get around with it. So in principle, this is actually deterministic. Then fidelity, not fidelity, I should say here. Fidelity is more like 1 minus this. And the key thing here is that this operation that we're doing, it's actually a spin photon gate rather than before where we had like this probabilistic entangling operation, right? That only if we're in the right state we would entangle it. What we're doing here is actually a deterministic operation. You can think of a gate between a photon and a spin in the sense that if I, for example, go in the Fock space encoding and say 0 photon, 1 photon is my qubit on the photon side, then, and I still have the 0 and 1 spin states, then what does this gate do? It says 0 photon, 0 just goes to 0 photon, 0. 1 photon, 0 goes to minus 1 photon, 0. 1 photon, whoop, 1 goes to 1 photon, 1, and 0 photon, 1 goes to 0 photon, 1. It's a C-phase gate in that encoding. So in principle, I can make a gate between a photon and the Fock base encoding here and my spin. And yeah, perfections are the same, just as before. It's the same operation kind of things that we have, but you have different couplings and whatnot. But I think one thing to take away here is that the phase space is kind of nice because it's deterministic and it's a gate. And if we care about more than just entangling operations, this gate becomes useful. We want to entangle some kind of photonic field that comes in with our spins. We want a gate, for example, if we want to map the information in there. So keep that in mind. Then just before we run out of time, I didn't talk about this scheme, the photon scheme here, entangled photon pair. But what I will give you as a little sign-off exercise for tomorrow, and we'll follow up on it tomorrow, is you're free to assume, idealized operation as we did for the other schemes, perfect reflection, zero reflection, whatnot. Choose what you want to do, phase, amplitude, whatever, both can work. How would you use, if you start with a photon pair, entangled photon pair, how will you use that to create spin entanglement in this case? You don't need to go through the math very carefully. What I'm just looking for is like, can you go through the steps of the protocol? What do you need to do? And just discuss kind of, how will the success probability be? Fidelity, we kind of know that will be something with this 1 over C, but just kind of that you have an idea about that. So feel free to discuss it in groups, whatever you want. But I would very much like that tomorrow, before we dive into the next topic, which will be more applications of quantum networks rather than repeaters, then we kind of just follow up on this, so we have it for completeness. All right. And that's it. So just again, kind of high level what we're doing, we looked at how do you do entanglement between spins mediated by photons. And there are kind of, different building blocks. You can do emission-based things. You can do scattering-based things. This is for you guys to figure out. That's kind of high level. You can then dive into the details of how exactly do you do these things. Like, for example, do you do amplitude or phase scattering? Do you do single click or 2 clicks goes and whatnot? And you could go even further down to exactly what operations you need to do on these. So it's kind of you zoom in, and what we didn't do is you can go even further down, right, to the imperfections that we didn't cover and say, okay, what about all these things that have been? So you can kind of, also the detection and whatnot. But what you can start to do is you can start on this level and say, okay, how do I high level see how I can make entanglement? Then you start to dive into exactly what operation you want to do. Then you start to dive into the quantum optical modeling. And then in the end, you have your description. So that way you can start to also play around with these things, combine emission with scattering based, amplitude with phase, whatever. Not sure it makes sense. You can check if there's any kind of trade-offs in your experimental system that would make it good on the other. For example, do you want to use one as a photon source, but with spin that you then just scatter off the other to get higher rates? Who knows? But yeah, that's it. And other things you can think of before tomorrow, it may be also a little bit some for preparation for tomorrow. Quantum networking applications, we just covered like bell pair generation. It's a little boring, right? I mean, okay, we did cover a little bit why do you want bell pair. It could be for QKD, it could be for demonstrating non-local entanglement and whatnot. But are there other things you want to use this for? Could some of these spin phone interfaces, for example, this gate we had in the end, could that be interesting for other things than just creating bell pairs? What could that be useful for? Didn't at all cover absorption on sample-based schemes, you know, so please do yourself a favor and look into that on your own time if you want to do that. I'm not going to cover it in any lecture tomorrow. I'm going to switch completely to applications there. Yeah, does it make sense to mix and match different things? In what case would you want to match these things using mono photon source and saying spin photon emission, for example, and whatnot? This we kind of discovered it, but indeed, if you really want to go out and go beyond what we did here, which is kind of a little bit high level, and you really want to look at the experiment, there will be tons of things that you need to look into, and some of this is not even very good modeled so far. There might also be actually new theoretical things you can look into there. Higher order correction terms that you can start to explore. They might not be relevant for the one experiment, but then that could be basically input to design an experiment to test these kind of things or look into things you can leverage these things as a new thing. Many more, you know, just think about it. All right. Thank you for your attention.